So what happened today? I see that like everyone's voice is so low, sleepy, not in mood or not energized. Okay. Anyway, so today we will discuss Bayesian network. Before that, I guess you all remember the Naive classifier or the Bayes theorem to say specifically. So Bayes theorem is basically based on the conditional probability. Uh, so as you can see in this example, so this is just for a just for to remembering the old things that we have learned. So by Bayes theorem, we try to find the class of the example or a data instance X. So basically, we try to determine the condition, the probability that X will belong to the class CK based on the probability of the class CK, and from our data set, what we have seen that probability of X given Ck by probability of X. So what we are trying to determine is that we know from data that X or example similar to X or the same type of X, what is their probability that given the class CK, that if we know a class, what is the probability that a particular data instance will belong there. We know the probability of the class, that is how large is the class, how many of the data instance it represents in the sample. And we also know the distribution of the data points, which is the probability of X. Okay. So from that, we try to determine that given a new data point, what will be the probability that it will be assigned to the class CK. And we do this over all the case and find the highest probability and we assign X to that class, right? So in other terms, this probability is, okay, let me show it from this. So this probability is called the posterior probability, that is coming posterior. This is called the prior probability. Prior probability is that the probability of the classes. So because we assume that the classes were generated first and then we create the X based on the class. So this is my likelihood. And this is my the evidence that how the what is the distribution of X in the data set. So this constitutes the Bayes theorem, and in the naive Bayes classification we have seen how we can use this Bayes theorem to do classification on the data having multiple features or a multivariate data set. Okay, I am not going to that. I think you already have the slides and it was discussed in the class. But please let me know if I need to revisit or re-explain any part of the naive Bayes classifier. Okay, because naive Bayes is a very basic classifier, and in future, in any kind of data science or machine learning that you do, you need to at least do as the back of your hand some classifiers like naive Bayes, random forest, and the maximum margin. Okay. So let us move into the Bayesian network. So actually, last few classes we covered the unsupervised learning, where we didn't know the class labels of the data instances, and we tried to group the data instances into different classes based on their like similarity or their distance. So we have seen the k-means clustering, hierarchical clustering. We have talked about the graphs, and also we have done spectral clustering, right? So actually, Bayesian network is not an unsupervised learning method. So we should have done it before unsupervised learning, but anyways, what's have been done is done. But one thing is that now we know that how we do machine learning or how we come up with a conclusion and we train models on the graph networks. So if you recall in the spectral clustering or the hierarchical clustering, what did the graph represent when we said we are constructing a graph network? So there was two pair of nodes. So nodes are typically the data instances and the graph edges represents the similarity or the distance between these two nodes or the two data instances. And we have worked on the undirected graphs but weighted graphs. Now in Bayesian network, we will see another type of graph, which are called the directed acyclic graph. So what is a directed acyclic graph? That unlike where the nodes are data instances and the graph edges merely represents the relationship or the similar, sorry, not relationship, the similarity or the distance among the two nodes. Here in the directed acyclic graphs, the edges actually denotes the dependency. That is the conditions or the cause and effect type of relationships. Okay. So in this case, the graphs nodes are the random variables and there is no cycle in the graph. That is why it is called the acyclic graphs. And why directed? Because these edges, they denote the dependencies in the graph. So basically now just instead of like the friendship the network like we have seen in the unsupervised learning when we were talking about the social networks or Facebook, here we have the ancestor and parent relationships. So it is more like a tree structure that there is the parents and the leaf nodes sorry, and from parents we have some children nodes. Okay, so each random variable x is independent of its non-descendants given its parents. So say for example, this is my x. So random variable means I want to calculate the probability of x given certain conditions, right? So this x, as you can see from the graph, it has two parents, y1 and y2. And this is the ancestor, like the parents of the parents, okay? And these are the non-descendants of x. That is, this one, it has no connection with x, therefore it is non-descendant. And this is also non-descendant, sorry, this is a descendant because it is coming from x, and these are also non-descendants from x. So what we say, that is the probability of x or the state of x or the value of x is independent of its non-descendant. That is, it is independent of these nodes, the non-descendant nodes. So there, from whom there is no pathway from x, given its parents. So x is only conditional on its parents. So now you can see there is a term that is written Markov assumption. So this is the Markov assumption. So we can treat the directed acyclic graph as a set of states. So these states uh, generates these states. These states is caused from these states, and Markov assumption says that this X is only conditioned based on its parents and is independent of the non-descendant. Okay. So more formally, we write like this, that is independent of x, non-descendant of x given the parents of x. Okay. So now we will see how we can actually work with this type of networks. Now let us see an example. So suppose we know that lung cancer is dependent on factors like smoking and and asbestos exposure. Now, we also know that smoking and asbestos exposure both have something or some relationship or dependency on the socioeconomic status of the person who is having lung cancer. Okay, so my Bayesian network can look like this. I want to determine, is there any relationship of lung cancer with the socioeconomic status of the person who has got it. So my network is socioeconomic status and it has two descendants, smoking and asbestos exposure with some probability values. And then smoking is also contributing to the asbestos exposure. And this socioeconomic status can also directly contribute to lung cancer, and there is also smoking and asbestos exposure that is contributing to the lung cancer. So this kind of graphical representation represents a Bayesian network. Like we can uh, computationally approach this from the Bayesian network's perspective. So why Bayesian networks? It is a simple graphical notation for conditional independence assertion. So via graph, we are showing that how each random variable uh, so what is like for each random variable, what are the other variable that is influencing it. So it is a compact specification of full joint distribution. So we know that naive Bayes or Bayes, these Bayesian networks are types of generative models. So instead of doing all the joint distributions via this type of graph construction, we can restrict ourselves to only a part of the conditional independences that we need to find out. So the syntax of a Bayesian network is a set of nodes, one per random variable, a directed acyclic graph where links indicate that directly which variables are directly influencing which variables. Say for example, just a moment. So say for example, in this network, you can very well ask the question that we are having the socioeconomic status influencing the asbestos exposure, which is in turn influencing lung cancer. Then why do we also have this arrow? Is it any different, or how is it contributing? The idea is that in the Bayesian network or in the directed acyclic graph, we construct a node if any variable or any parent is directly influencing a random variable. Okay, so making its descendant. So in this case, we may have a value. Say for example, some people did a survey and they found a conditional probability that uh, like the socioeconomic status of persons given lung cancer. So they have the this likelihood. So that is why we have this direct influence from socioeconomic status to lung cancer. So we have constructed this at arrow. So in this way, all arrows or all links are constructed based on the direct influences. Okay. And for each node, a conditional distribution is given based on its parents. So we have this probability value xi given parents of xi. Now from where do we get the conditional distributions? These are represented as a conditional probability table or CPT. We will see it in the next slides. So what does the CPT give? The distributions over xi for each combination of parent values. Okay, so if as say for example, uh, this node, lung cancer, or say let us take this example, this the asbestos exposure, it has two parents like smoking and socioeconomic status both. Okay, so this when my conditional probability table will give the probability for asbestos given all the combination of smoking and socioeconomic status. Like if smoking is there, but socioeconomic status, say we have categorized it into high and low. High, smoking for low, no smoking for high, no smoking for low. Okay, this kind of thing. And just remember, a node is independent of its non-descendants given its parents. Now let us see one example. So say we have some variables like the weather, cavity, toothache, and catch. Now the topology of the networks, the encoding these random variables will be looking like this. Because weather is completely independent of the other variables and it is also not influencing the other variables. So your toothache is not dependent on the weather. Whereas toothache and catch both are conditionally independent given cavity. So toothache given cavity and and catch given cavity are conditionally independent of each other. So what does that mean? That toothache and catch, so we can calculate their probabilities separately and the occurrence of one does not affect the occurrence of other. Given cavity, given that there is already the pre-existing condition of cavity. So let us see an example use case. So say this is a statement that I am at work. Neighbor John calls to say my alarm is ringing, but neighbor Mary doesn't call. Sometimes it's set off by minor earthquakes. Is there a burglar? So I want to find this answer, that what is the probability that there is the burglary at my home given multiple things. My house alarm has been set off or not set off. John has called, but my other neighbor Mary hasn't called, and the alarm can also set off by minor earthquake. So that means for burglary, the condition needs to be the alarm has actually set off, which John has heard. Mary may or may not have heard, but didn't call, and there is no earthquake. So in this case, what are my variables? First of all, I need to find a probability of the burglary. So burglary is a variable. I need to find that the probability that there was no minor earthquake. So earthquake is also a variable. Then the probability is there that the alarm has been set off actually. So alarm is a variable. And then John calling on alarm being set off is a probability. So my John calls is a random variable and my Mary calls is also a variable. So now my network topology should reflect the causal knowledge that a burglar can set the alarm off and earthquake can also set the alarm off. The alarm can cause Mary to call, the alarm can cause John to call. So these are my causal knowledge that I know. Okay. So based on the knowledge and based on the variables, I construct these Bayesian networks. So let us see. The first is that at the alarm. So burglary can directly influence the alarm. So there will be a link. Earthquake can also directly influence the alarm. So there will be another link. And burglary and earthquake are not dependent on each other. Okay, so there is no link among them. Then the alarm can cause John to call. Then John is a link. Alarm can cause Mary to call. Then so there is a link, it directly influences. But John calls and Mary calls, so John calling and Mary calling are conditionally independent given the alarm has been set off. Okay. So now we were talking about the conditional probability tables. This is what the tables look like. Say for burglary, there is no parent. So probability of burglary is 0.001. So these probability values, these are already given. So we have some database and we know that in that region, the probability of burglary is this and the probability of earthquake is also this. Now for the alarm, we have two parents. Now we know that the conditional probability table gives the probability of the variable given all the combination of its parents. So what will be the combination for burglary and the earthquake? Now remember the Boolean tables, the Boolean logic 0, 1. So how did we do? For both to be true, for one to be true, another to be false, for the first one to be false and second one to be true and both to be false. That is 1, 1, 1, 0, 0, 1 and 0, 0. And we have all the conditions for the all the probability for the same given. So for the alarm to go off, it will be alarm to ring when both are true, it is 0.95, very high probability, and when both are false, the alarm can still go off, but with a very low probability. That is, it is highly unlikely to occur. And then for John and Mary, similarly, we have these two conditional probability tables. So John calls if the alarm actually goes off is 0.90 high probability. John can call if the alarm didn't go off, but if John feels actually he has heard something. So this is also a non-zero probability. Okay. So this is how we construct a Bayesian network and based on this kind of the use case and the causal knowledge. So any question till now? Yes, no? Are people listening?
No.
Okay, so let us move forward. So let us see, we stated that we go for the Bayesian networks because it is a compact specification of full joint distribution. So let's see what does this compactness actually means. So now for a random variable xi, a conditional probability table with k Boolean parents. So why the Boolean term is used? If you see this, the alarm is only has two states. Either it can go up or it don't. For burglary, it also has two states. Either it happens or it don't. For earthquake also it is two states. Either it happened or it don't. Similarly for John calls and Mary calls. So that is why we are saying this the Booleans because it is only 0 and 1. Okay. So now this xi for each Boolean xi, if it has say like k parents, which are again the Booleans, so it will have 2 to the power k rows for the combinations of parent values, correct? We know it from the Boolean algebra that say there are say three Boolean variables. That means only having the values zeros and ones. So how many combinations can there be? 2 to the power 3, that is 8. That's how we also compute the numbers of discrete numbers, say a 128-bit memory can represent, correct? So the basic of the logic gates. Okay. So say for example in the alarm, it is a Boolean variable and it has two parents which are again Booleans. So how many combinations? 2 to the power 2, that is 4. So 4. Correct. Now each row only requires one number p for xi to be true, because as it is Boolean, the number for xi to be false is just 1 minus p. See, in this case, when we say that probability of the alarm b comma e in this condition is 0.95, that means what? That probability of the alarm is going on if both are true is 0.95. That means the alarm value is true. Now, if I say the probability of the alarm not going off when both are true, it is just 1 minus p. So we don't need another table for the not or another column for the not a. Okay. Now, if each variable has no more than k parents, say this is some condition or this is some constraint that we implement of the graph. Say at max, a variable can have say 3 parents. So the complete network requires only n into 2 to the power k. Say for example, if I have fixed k to 3 or my network is fixed at max k to 3, so then it will be maximum of 8 CPT values, maximum of 8 rows in the CPT for each of the variables, and for the n variables that will be the n into 2 to the power 3. So the main point is that this requirements only grows linearly with n. Whereas if we want to go for a full joint distribution without imposing the Markov assumption, that if we say that we need to have all the probability values for all pairs of nodes, how many we will have for n Boolean variables? It will be 2 to the power n, right? So this is growing exponentially with respect to n. For example, for this burglary net, how many numbers we require? See, this has no parents. So it will be order of 2 to the power 0, that is 1. This is also 2 to the power 0, the number, so 1. So 1 plus 1. This has two parents, so 2 to the power 2, that is 4 numbers in the conditional probability table. This has one parent, so 2 to the power of 1, so 2 numbers, and this has one parent also, so 2 to the power of 1, so 2 numbers. So total we are only needing 10 numbers in my CPT. See, 1, 2, 2 plus 4, 6, 6 plus 2, 8, plus 2, 10. Whereas if for the 5 variables, I would have gone for the full joint probability distribution, that would have been my 2 to the power 5 minus 1, that is 31 numbers. So you can see, like for large networks, order of say like hundreds or thousands of nodes, these reduces my computation and makes it compact to a great length. Now,
Ma'am, can you explain the second point again?
which one? Tell me.
Second one. Each
This
row
one.
requires.
This one. This one, right? Each row requires.
Yes, yes.
Yes. Yes. So what we are saying, say I am assuming that my random variable is a Boolean variable. That means it can only have state 0 and 1. That is occur, doesn't occur. And its parents are also the Boolean variables. That means the parents can either be true or can be false. So what happens in this table? Say for example, if someone asks you that what will be the probability that the alarm doesn't go off given burglary and earthquake both has occurred, and alarm can malfunction, like, right? So how would I find this out? Because my alarm has only two states, so this is true. This is P equals to like P of the alarm given both burglary and earthquake to be true. If it is 0.95, then what is the chance that it hasn't occurred? The total probability is 1 in all situations, right? So it will be 1 minus this P given P of A given B comma E. So it will be 0.05. So in this way, we are not required to have say another column which will be 4 more numbers for the not occurrences of the at the alarm given the same condition, because we know that it is a Boolean variable. So if we just have the value for true, we can have the number for false by just doing this 1 minus P. Am I correct?
Yes, yes, I got it.
Okay. Okay. So now let us see that how we define the actual full joint distribution on a Bayesian network. Because at the end, what we are trying to find is a full joint distribution. That means, say for example, in this case, there was a burglary and the alarm went off and the earthquake didn't happen and John calls and Mary didn't call. Okay, so this is what I am interested to find. Now, how do I find the full joint distribution over a Bayesian network? We have said that only a random variable x is only dependent on its parents. So all the conditional probabilities are local, and two random variables like j and m, which does not have a direct link, are conditionally independent. So what does conditionally independent mean? The joint probability is just the multiplications of the individual probability, right? So that means P of x1 comma xn, that means the joint distribution of all the random variables is actually the multiplication of each pi given its parents xi. Sorry, each p of xi given the parents of xi. That means, say for example, this will be probability of burglary, probability of into probability of earthquake into probability of A given B and E into probability of J given A into probability of M given A. In this way, we find the full joint distribution of the Bayesian network. Say for an example, I want to find what will be the probability that J calls, Mary calls, the alarm has went off, but a burglary didn't happen and also an earthquake didn't happen. See, so it will be joint probability of J and M and alarm and not B and not E. So how will we compute this? We know that probability of J is only dependent on A. So this will be probability of J given A. Probability of M is only dependent on A. So it will be probability of M given A. Now we know that this J and M are both conditionally independent given its parents. So probability of joint probability of J and M will be probability of J given A into probability of M given A, correct? And then we have also the probability of A. Now we know that the probability of A is dependent on its two parents, and the conditions are given as not B and not E. So we will need to find the probability of A given not B and not E, and then the probability of not B and probability of not E, because again the probability of B and E are conditionally independent of each other. Okay. So, and also a node is independent of its non-descendants given its parents. So basically, this whole joint probability comes down to the multiplication of these local conditional probabilities, and this we can find it easily from this CPT table. So clear till this point?
Yes, ma'am.
So what will be the actual value of this? Let us calculate. Can you write down this equation? So let us see probability of J given A, sorry, is 0.9. Probability of M given A is 0.7. So 0.9 into 0.7, 0.63. Probability of A given not B not E, that is 0.001. It will be 0.00063, and then probability of not B is very high, so it will be how much? This is 0.999,
0.999.
and it will be 0.998. Now my spoken math skill has gone. So if you multiply this number, that will be the probability of this full joint distribution. Okay. Yes. I think someone has written something, the number in chat. So thank you. Okay. Okay. So now, till this point, we had a Bayesian network, we had the CPTs, and we have constructed. And we have found the full joint probability distribution. Now, in the next part, how can I construct a Bayesian network? See, why there is a need to have a methodical approach for Bayesian network construction? Because see, in this case, this was only 5 variables, and this is relatively the easier case study. So we were able to construct it by hand. But say when there will be something like say 50 variable or even 10 variables, it becomes difficult to actually construct like just by like all the combinations and trial and error manually. Okay. So let us see uh, how can we construct a Bayesian network given a set of variables and the parent-child relationship. Okay. So first step, choose an ordering of the variable x1 to xn because we need to assign the some numbers. So now by iteration from I is equal to 1 to n, add xi to the network and select parents from x1 to x minus xi minus 1 such that probability of xi given parents of xi equals to probability of xi given x1 to xi minus 1. Now this is an example of it actually implementing the Markov assumption. So what are we doing? We are ordering the variable in any way from x1 to xn. Now we are writing down a for loop kind of thing. So we need to iterate. So we cannot iterate randomly. So that's why the ordering is needed. So say for example, I pick now my I is equals to 4. So I need to add x4 to the network. Now when I need to add x4 to the network, that means I need to establish some connection from parents to x4 or x4 to its descendants. Okay. Now, as I have said, the conditional probabilities, as we have seen, these are only dependent on parents. So parents are the most important part. So how do I need to select the parents for x4 from the set x1 to xi minus 1, that is x1 to x3, such that parent of the probability of x4 given the parents of x4 is equal to the probability of x4 given x1, x2 and x3, because that is my objective, right? So in a network, my conditional probability of a random variable given its parents is actually uh, the indicator of the probability of the random variables given all other nodes in the network. Now, the choice of the parent, it also guarantees that the full joint probability distribution is actually the multiplication of the local conditional probabilities by chain rule. Okay, that chain rule now, do you remember the example of language models when the Bayes theorem was discussed? I see it is in the slides, but do you actually recall that? Okay. Okay, so just let me explain. So what chain rule says, as you can see, if you expand this equation, it becomes P of x1 into P of x1 given P of x2 given x1, P of x3 given x1 and x2 into P of x4 given P of x1, x2, x3, dot dot dot. So P of xn given P of x1 to P of xn minus 1. So like a chain. So as we are so we begin with the x1 and the probability of x1 is x1. Now we bring in x2. So now the joint probability of x1 and x2 is probability of x1 and probability of x1 given x2. Now we add x3 to the chain. Now the joint probability of x1, x2 and x3 becomes probability of x1 into probability of x2 given x1, because I have added x2 given x1, and probability of x3 given probability of x1 and x2. But the only computational problem in this is that it is growing exponentially. So as you add 4 nodes, that means you need to calculate all the conditional probability based on x1, x2, x3. So again, it is going to the full joint distribution mode. So now, if I make the choice of the parents, and if we assume that the value of any xi is only dependent on its parent, so we can break down this chain rule into a multiplication of the conditionally independent probability distribution. So we say for any random variable x, it is only dependent on its immediate parent, and that is the Markov assumption. That means probability of x1 is there, but probability of x2 will only dependent on x1. Probability of x3 will be only dependent on its parent. If it is x2, then x3 given x2, and if x1 is its immediate parents, then it will be x3 given x1. So by construction, we actually, from the chain rule, we make it to the multiplication of local conditional probabilities. Yes, sir. Any question?
Ma'am, you mean you are expanding that expression using the chain rule, and then the independent variables automatically become 0 and we get the other equation.
Yes. So what I am saying that by chain rule, this will be my actual expression. Now, as I am making a Bayesian network and I am imposing the Markov assumption, so this chain rule calculation actually becomes this, like we have seen in this case. We just did now. Okay.
Yes, yes.
Because if we have gone for the chain rule, See, my probability of J, A and E would have been probability of J given A and E into probability of A given E. But in this case, what we are doing, it is only probability of J given A into probability of A given E. Just the multiplication of the conditional probability based on the immediate parents. Okay. So let us again go back to the same example and let us see how can we construct a Bayesian net. So suppose we chose the ordering of the variables M, J, A, B and E, that is Mary calls, John calls, the alarm goes off, burglary occurs and also earthquake occurs. So we start with say Mary calls and John calls. So my question is that whether P of say we first picked Mary calls, so there is no age. Now by this iteration, the next random variable is John calls. So I add John calls. Now how do I establish the connection? My first question is that whether P of John given Mary, that is P of John, probability of John calls given Mary calls, is it equals to the probability of John calls? No. We know that probability now. And okay, and then we add the node of the we add the node for the random variable alarm. So now for the alarm, I need to see that whether the probability of alarm, like this part, that is the probability of alarm given John and Mary. So is it equal to probability of alarm given John, or the probability of alarm given John and Mary is equal to the probability of alarm? So this is also no. So I think I am missing some point here. Okay. So let us continue it to today's class. Okay, because it will take some time, because this network is basically the inverse of the other network. So in this case, we are actually trying to find out the so it is basically our network represent that if say Mary calls and John calls and the alarm goes on. So what is the probability of the burglary and the earthquake? So that is why I stopped at first, that because we were just seeing the exact opposite, that what is the probability that John calls and Mary does not call given the alarm went off and the burglary happens and the earthquake happens. So we will discuss this construction in tomorrow's class, because otherwise what we have discussed till now and this one, it will be completely messed up. Okay. So thank you.
Ma'am.
Any question? Yes. Yes.
But now that we are constructing the network, like shouldn't we be provided with the table first?
Yes. 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 We actually, this table is something that we assume that it is there. So we are not calculating the individual conditional probability right at this moment. So we are focusing on the construction at assuming that these values are there. That assuming that we know this beforehand.
So the network that you are constructing now, so the table for that will be different from the one that we discussed before this, right? Because we have a different network here.
Yes, yes, yes. We like not in the sense different networks, but different. We are now calculating different types of probabilities. So,
Uh, no, I mean, like the connections in this
yes,
network
yes,
that you have
yes, yes,
shown
yes.
are different,
So
right?
what you are saying is correct. So what I wanted to say that tables will be different because the conditional probability those are being calculated are different. So my table entries are different.
Yes,
But the tables will be same type as we have seen, like based on the parent and the direct descendants.
yes,
So did I answer your
yes, I got it.
okay, okay. Okay. So any more question?